So welcome to the second part of Math 355 Lecture 11. What I want to do now is I want to shift to cryptography. Does not seem like it is. So that's sharing screen. We're showing something else, sharing the screen. Okay, let's try it again. Welcome to Math 355. There you go. Okay. So this is Introduction to Cryptography. So we're going to start by seeing some things that we have seen before, and then talk a little bit about some of the generalizations and where group theory comes into play to allow us to do RSA encryption. So for years, RSA encryption was the gold standard, and we've already done enough so that we can see why this works. I'm not going to give the most efficient proofs of results because I want to use this to motivate some of the material we're doing in group theory, but more than that, to just highlight how do you prove things in mathematics. I want to talk about the thought process. All right. So let's quickly review what RSA was. So we saw this in the first class. You are required to have Alice and Bob exchanging messages. Usually Alice sends a message to Bob. The only freedom you have is it can be either Charlie or Eve who's trying to eavesdrop and figure out the message. And so the way it works is Bob chooses two large primes, P and Q, and keeps them secret. Just so I can write everything down on the slides, my primes are not huge. You should think of these as 200-digit numbers, okay? There are less than 10 to the 100 objects in the universe. This is dwarfing anything here. And the idea is to show you that what initially looks to be such a computational nightmare that there is no way we should be able to do it, it turns out we can actually do all these calculations in a reasonable amount of time. This is why e-commerce can exist. This is why certain codes can be secure. If quantum computing becomes practical, however, systems like this will no longer be secure. Okay, so Bob chooses two primes, P and Q. He chooses some number D, and he chooses the number E in a very special way. And he's going to make E public, and he's going to make the product of P and Q public, although he's going to keep P and Q secret. And E was chosen so that E times D is 1 mod P minus 1 Q minus 1. So it's not clear that there's going to be a way to do this, but we will assume that you can, and then we'll later discuss just how difficult is it to do all these steps. And then let's say you want to send a message. So I claim that it's enough to send numbers rather than sending letters. So let's look at blocks of 2 digits. So maybe 00 is lowercase a, 01 is lowercase b, 25 is lowercase z, maybe 26 is uppercase a. We do this all the way to 51, and then maybe 52 is 0, 53 is 1, and it gives me another 9 ones, and then maybe the next couple of ones are punctuation marks and special symbols. So is everybody comfortable that it's enough to just send numbers? We don't have to send letters? That's okay? And so if your message is bigger than n, capital N, the product of P and Q, you just break it up into blocks of size and just keep sending the blocks. And what Alice does is she takes her message and she raises it for the eth power, E for encrypt. And she sends n to the E mod n to Bob. Now, if E is 10 to the 400, this means Alice has to do 10 to the 400 multiplications. That is way beyond anything a human can do. You're a supercomputer. You're lucky if you can do 10 to the 200 objects. If every object in the universe, say there's 10 to the 80, 10 to the 90 objects. If every object in the universe was a universe, and every object in that universe was a universe, that gets you to maybe 10 to the 180. And we need to get to 10 to the 200. This should show you just how unbelievably difficult this is. But we're pure mathematicians right now. We will just say, Alice does it. She raises m to the eth power. She sends the remainder when she divides by n. And she sends 121209473 to Bob. Bob takes that and raises it to D for decrypt and looks at this mod n and amazingly gets the same number as Alice. As a nice exercise, I urge you to find some computer software system where you can actually do this calculation and see that it works. That's one of the reasons why I chose these numbers to be modest. If I chose primes like 3 and 5, you can just do it by hand. These numbers are at least large enough that you have to work a little bit. But see if you can do it. See if you can actually make the calculation work and see that you get the number. Okay. Now, whenever you're raising something to the nth power, if you're doing a bunch of multiplications, you can always reduce mod n every time you do a multiplication. So your number is never going to be larger than, say, n squared. But that's still a lot of multiplications to do. It turns out this message has a lot of advantages over the classical encryption we saw in the first class when we did things like the Caesar cipher. If you shift all the letters by 3, this is pretty easy to decrypt. But if you get one letter wrong in your message, you can still figure out what's going on because you have every letter but one correct. Imagine Bob receives one digit wrong. Well, he's now raising that to the dth power. If even one digit is wrong, then the message is going to be completely different. So now I chose the second to last digit to be 8 rather than 7. When he raises it to the dth power, he gets 121141028. Only 2 digits are the same as the original message. Well, imagine we choose some message, and I choose a bunch of random digits. What do you think the probability that my first digit matches the first digit of the message is? So how likely should my first digit equal the first digit of the message? 110. So if my message has 500 digits, how many digits would you expect to match? Well, approximately how many? Let's quantify not very many. If there's 500 digits, about how many should match? I'm sorry? No. You have 5. I'm looking at, do the first digits match? Do the second digits match? Do the third digits? How many digits are the same? The same digit in the same spot. You just said I have a 1 in 10 chance that a digit matches. So if there's 500 digits, how many matches do you expect? 50. So I was sending a 9-digit number. So I would expect about 0.9 or about 1 digit to be the same. And if you look at the garbage that Bob got because 1 digit was off, he had 2 digits right out of 9. Well, if you expect to have 1 digit right, getting 2 digits right, that's ballpark what you would expect. You always want to do calculations and see, is this reasonable? And what we're seeing here is that, yeah, this is actually reasonable. If even one thing is slightly different, it's essentially like you've got noise. You have no information. So there's a lot of implementation issues. How do we find large primes? How large is large enough? You're probably not going to get to that today. How do we find an E and a D so that E times D is 1 mod P minus 1 Q minus 1? How do we compute M to the E mod N efficiently? And then the hard one, which is still open, can Eve determine D from E and M? So, again, we've made public the product of the 2 primes. We've made public the E for encrypt. Is there a way to figure out what the primes are? Is there a way to figure out what D is? To date, nobody has published a way to do that. If there is a way, no one has stated they know it. Okay, so what I want to do now is I want to prove Fermat's little theorem. There's another theorem that's often associated to Fermat. Does anybody know what that theorem is? Fermat's last theorem. We use a capital L to abbreviate Fermat's last theorem. We use a lowercase l for Fermat's little theorem. We've actually seen Fermat's little theorem already this semester. We saw it a little bit on the first day of class. It's actually a consequence of a theorem in group theory. But I want to give a separate independent proof of just Fermat's little theorem because it's nice to get a sense of how deep is a result. Does it really need all these results in group theory, or can it be proven with a little bit less? It also gives me an opportunity to show you how mathematicians think and to show you another way of attacking problems. So just a little bit of notation. We saw this on the first day of class. Let phi of n denote the number of integers from 1 to n that are relatively prime to n. So for example, phi of p would just be p minus 1. Because if I want to look at it, if p is a prime, then the numbers from 1 to p that are relatively prime to p, the only one that shares a factor with p is p. If, however, I take two distinct primes, p and q, then it's going to be p minus 1, q minus 1. The way to see this is I lose all the multiples of p, so I lose p, 2p, 3p, all the way up to qp. I lose all the multiples of q, q, 2q, 3q, all the way up to pq. And then I subtracted the multiple pq twice, so I have to add one back. So when you do the algebra, and we did this on the first day of class, and the dust settles, it turns out it's just p minus 1 times q minus 1. We don't need, but you can prove that if m and n are relatively prime, then phi of the product is the product of the phis. If you have p to the k, it's p to the k minus p to the k minus 1. And the reason is we lose all multiples of p, and 1 over p of the numbers are multiples of p. That's how you should view p to the k minus 1. It's 1 over p times p to the k. There is a lot of group theory lurking in the background. Since this is a class on group theory, I should be excited, right? But I want to try to see what can we do without using group theory. So let's look at Fermat's little theorem. It says if a is relatively prime to n, then if you raise a to the phi of n, you get 1 mod n. So the two special cases that we'll need is the first case is when n is a prime p, you get a to the p minus 1 is 1 mod p. And the second is if n is equal to p times q, then you get a to the p minus 1 q minus 1 is equal to 1 mod pq. Does this remind you of any theorem from group theory? We have a theorem that is similar to this. So imagine you have a finite group and you choose some element a. And you can look at a squared, a cubed, a to the 4th, a to the 5th. If you look at all powers of a, what does that give you? It gives you a cyclic subgroup. And what can you tell me about the order of a subgroup? It divides the order. So whose theorem is this? This is Lagrange's theorem. It's a beautiful theorem. The order of a subgroup divides the order of a group. So if we know that the numbers relatively prime to p form a multiplicative group, the order of that is going to be p minus 1, and there you go. If we know that the numbers that are relatively prime to pq form a multiplicative group, and the number of elements is p minus 1 and q minus 1, there's the second one. This is just Lagrange's theorem. But if we want to use Lagrange's theorem, we need to know that these are multiplicative groups. And to do that, we actually needed to use the Euclidean algorithm to prove that we have inverses. So for instance, if I'm looking at p equals 7, then 5 is invertible. Anybody know what the inverse of 5 mod 7 is? 3. 3 times 5 is 15, which is 1 more. So I'm not going to use Lagrange's theorem, but you could get this result by using Lagrange's theorem. I want to talk about how to prove these more directly. I'll emphasize what do you need to assume. We're not using the Euclidean algorithm, but we are using something else. And then this will highlight a really great proof technique. If you need a one word to describe mathematicians, that word should be lazy. Whenever possible, mathematicians try to reduce whatever you give them to something they already know how to do. So you try to do a simple case, and then you reduce the complicated case to the simpler case. That's why I want to do this proof today, because it allows me to highlight that idea. So let's first do the case when n is a prime. So in this situation, we start off with a prime p. We choose some element a that's relatively prime, and we consider the numbers 1, 2, 3, all the way up to p minus 1. And I multiply all of those numbers by a. So I claim that both of these sets have p minus 1 elements. That's easy. And I claim when you look at their remainders mod p, they're all distinct. Well, the first set is kind of easy. right? The numbers are 1, 2, 3, all the way up to p minus 1. When I look at their remainders mod p, I just get the number back. So clearly, the ones on the left are all going to be the same. It's the right that's more interesting, that all the numbers on the right are distinct mod p, that it's just the same numbers as the ones on the left, just potentially reordered. Now, it's very important here that p is a prime. If I choose, for instance, a to be 3, and maybe I have n equals 12, 3 times 4 is the same as 3 times 8. So even though 4 and 8 are different, they have the same remainder mod 12 when I multiply by 3. So it's essential here that p is a prime. So how would we show that these numbers a, 2a, and so on, how would we show they're all distinct? So how could we show that they're distinct? What could we try to do? So if they're not distinct, what would that mean? So there's either two possibilities. They're either all distinct or they're not all distinct. And so if they're not all distinct, what must be true? Two must be the same. So let's say I times a equals j times a mod p. So that means I minus j times a is 0 mod p. So that means I minus j times a is a multiple of p. So the prime divides the product. That's the key input we're going to use here. If a prime divides a product, then it has to divide one of the factors. We know the prime can't divide a because we chose it to be relatively prime to a. So the only thing that's left is the prime has to divide I minus j. Well, that means I is the same as j mod p, so my numbers are distinct. So if I look at the remainders of a, 2a, 3a, all the way up to p minus 1a, it's the same as the numbers 1 through p minus 1, just potentially in a different order. So if I multiply the two sets, they have to be the same number. So when I multiply the left, that's pretty easy. It's just p minus 1 factorial. When I multiply the right, I have p minus 1 factorial, but each factor also has an a. I have p minus 1 of them, so I get an a to the p minus 1. And so now look, I've got p minus 1 factorial equals p minus 1 factorial a to the p minus 1 mod p. Because p minus 1 factorial is not a multiple of p, we proved we have the cancellation property. Or you could just subtract the two sides, and since p doesn't divide p minus 1 factorial, we would have to divide 1 minus a to the p minus 1. And from this, we can now deduce that a to the p minus 1 is 1 mod p. So this is a proof of Fermat's little theorem. The key input was if a prime divides a product, then it divides one of them. We did not have to prove that we had a group structure. Okay. As a nice exercise, I'll leave this for you to think about. Can you do the general case? What if we have some integer n which is not necessarily prime? So we can write down what the what the multiplicative elements are. And so maybe if I'm doing things mod 12, I'll write down the elements that are relatively prime to 12. So it would be 1, 5, 7, and 11. So here x1 would be 1, x2 would be 5, x3 would be 7, x4 would be 11. And can you generalize the argument we just did for that case? So that's an exercise for you to think about. Can you take this argument and make it work over here? What was nice in the first case when we had a prime is I knew what my residues were. They're just 1, 2, 3, all the way up to p minus 1. Once I give you a general n, it's a little bit harder, and I just have to use abstract notation. Okay, let's consider Fermat's little theorem now, and let's try to prove it in the special case when n is a product of two distinct primes p and q. So I want to use Fermat's little theorem, and I'm going to use it twice. So if I use Fermat's little theorem, I need two inputs. I need a prime, and I need a number relatively prime to the prime. So can somebody give me a prime that I could try to use? So n equals p times q, and a is relatively prime to p and q. I need a prime. I'm sorry? Y3. Right, but look at what we have. We're trying to prove Fermat's little theorem when n is p times q. What would be a good choice for a prime? P. And there's one other good choice. Q, right? I know we've already proven Fermat's little theorem when we have a prime P. So I can use the prime to be P, I could use the prime to be Q. The other input I need for Fermat's little theorem is I need an integer relatively prime to P. So we know A is relatively prime to P and Q, right? So I could use A. Is there anything else I could use that's related to A that would be relatively prime to P? So A is relatively prime to PQ. I can use A, but there's something related to A that I can also use. So can you think of something related to A that we could try? Can I do A plus P? I could. But what else could I do? I could take A, and how could I combine A with A? What could I look at? This is the hard step. Well, A mod P is really the same as A. I might as well assume A is less than P. What operation can I do with A and A? So how could I combine A and A and get something that's relatively prime to P? I could take A squared. And after A squared, what could I take? A cubed. And why might I want to do this? Well, look, I'm trying to show A to the P minus 1 to Q minus 1 is 1 mod PQ. Well, Fermat's little theorem says take something relatively prime to P and raise it to the P minus 1 power. I've got A to the P minus 1 times Q minus 1. How many powers of A should I take? I'm sorry? To Q minus 1? I don't want to take it to their product because I want to raise it to the P minus 1 power. So I want to take A to the Q minus 1 power. And if I do that, then it's going to work out nicely. And so I'll apply Fermat's little theorem twice. First, I'll apply it with the prime P and A to the Q minus 1. Then I'll apply it with the prime Q and A to the P minus 1. And again, this is the main part I want you to get from today's lecture, that this is a natural thing to try. And when I do it like this, I'm being lazy. I know Fermat's little theorem when I have a prime. And so what I want to do is I want to use it twice. I have two different primes, and I have some freedom. And what's nice now is when I take the first case and I raise it to the P minus 1 power, that's the same as the second case and raising it to the Q minus 1 power. So these two expressions are the same. So I get A to the Q minus 1 P minus 1 or A to the P minus 1 Q minus 1 is 1 mod P, and it's also 1 mod Q. I'm trying to show that it's 1 mod PQ. So all I have to do now is I know it has a remainder 1 when I divide by P. I know it has a remainder of 1 when I divide by Q. I now just have to show that it has a remainder of 1 when I divide by PQ. Well, because it has a remainder of 1 when I divide by P, I can write it as 1 plus alpha P. And similarly, I can write it as 1 plus beta Q. So if I want to show that it is divisible by P times Q, what do I have to show about alpha? So we already know we can write it as 1 plus alpha P, and that's going to give me something that's a multiple of P, that's 1 more than a multiple of P. If I want to show that it's one more than a multiple of PQ, what must be true about alpha? It's got to be a multiple of Q. And similarly, beta must be a multiple of P. So I hope you can hear the equation screaming at you what to do. You've got 1 plus alpha P equals 1 plus beta Q. Let's just subtract 1 from both sides. And when you do that, you get alpha P equals beta Q, but P and Q are distinct primes. And so again, we use, if a prime divides a product, it divides at least one of the factors. Since P doesn't divide Q, P has to divide beta. Since Q doesn't divide P, Q has to divide alpha. And therefore, we get that our expression really is 1 mod PQ. And so we were able to prove Fermat's little theorem for 2 primes by using Fermat's little theorem for 1 prime twice in a really good way. Is we have some freedom in terms of which input do we use as the number relatively prime to our prime. Okay, I'm not going to go through the primality test. We talked about that in the first day of class. This way, if anybody ever hits pause on the slides, in the video, it's there. All right. What I want to do now is I want to turn to fast multiplication. If we can't calculate on these high powers quickly, then RSA is for all practical purposes useless. I don't care how much money you have, I don't care who you have as friends, you do not have a universe of universes of supercomputers devoted exclusively to your use running since the dawn of the Big Bang, right? If we need something as powerful as that to make any progress, we're just dead. So let's get a sense of how expensive operations are. You always want to get a sense of what is the meat, what is the part that really matters. Imagine I give you a 100-digit number and I give you another 100-digit number. How many digit operations are there to add them? About 100, maybe 200 because I might have carries. But basically, if I give you a D-digit number and another D-digit number, it's either D or 2D additions to add them. So the number of operations is linear with the number of digits. Now let's look at multiplication. If I have a 100-digit number and I multiply by a 100-digit number, how many multiplications of digits do I have? So I have a 100-digit number, I have another 100-digit number. How many multiplications do I have to do the digit operations? A 100 times 100, 100 squared. Each digit hits all the others. So in general, if I give you 2 D-digit numbers, it's D squared digit operations. So there's so many more multiplications than additions when you add 2 numbers versus multiplying them, that for all practical purposes, we say adding 2 large numbers, the addition is free. If we multiply numbers, it's just the multiplication cost that matters. The addition cost is negligible. So let's look at a polynomial. This is not a polynomial of high degree. I wanted to be able to write it on the board. This is a quintic. It's a degree 5 polynomial. How many multiplications does it cost to calculate 3x to the 5th? So how many multiplications does 3x to the 5th cost? 5. X does still say it's recording. So it still says it's recording. So hopefully we just lost the transmission, but it should still be okay. All right. So if I want to calculate how many multiplications are there for polynomial of degree d, I could do it by induction, or I could take the numbers 1 through d, and if I write them backwards, d down to 1, when you add them component by component, 1 plus d is d plus 1, 2 plus d minus 1 is d plus 1. I have d of these, so the sum is d times d plus 1, but I've counted every term twice, so if I divide by 2, I get the claim. Here is the fast way to do polynomial evaluation. This is essentially the best you can do in general. It's amazing. When I was in school, they taught math, and they taught stuff like this when I was in maybe junior high. I forget exactly when I first saw this. It's all about grouping things intelligently. If you want to evaluate a polynomial, to calculate x to the fifth, if you're doing x times x times x times x times x, that's wasteful because you've already calculated x to the fourth. And if you're calculating x to the fourth, that's wasteful to do x times x times x times x because you've already done x cubed. So why not build on this and don't keep redoing the same calculations? And so what we do is we factor things out. And so we do 3x minus 8, and then we multiply that by x. Then we add 7, and we multiply that by x. Then we add 6, and we multiply that by x. And then we subtract 9, and we multiply that by x. And then we add 2. And if you now expand everything out, the 3x hits the orange x, and the green x, and the blue x, and the red x. That gives you your 3x to the fifth. The negative 8 hits the orange x, the green x, the blue x, the red x. That gives you negative 8x to the fourth. The 7 hits the green x, the blue x, the red x. That gives you 7x cubed. So this is the same polynomial as what we had before. But now, rather than having 15 multiplications, the 3x gives me 1. So that's 1 times the orange x is 2, green x is 3, blue x is 4, red x is 5. Now I only have 5 multiplications. So rather than having on the order of d squared over 2 multiplications, I only have on the order of d multiplications. That's an incredible savings. Now the problem is if my exponent is 10 to the 400, okay, if I square that, that's of size 10 to the 800. 10 to the 400 is a lot less than 10 to the 800, but 10 to the 400 is still much more than I can do. So even though it's a savings, it's not enough of a savings to make things practical. Okay, so, but it's progress. So Horner's algorithm is essentially the best that we can do in general, but maybe if we have a very special polynomial, maybe we can do better for special polynomials. And so my question is, can you give me a really nice polynomial of degree n? The simplest polynomial of degree n you can think of. Simplest polynomial of degree n you can think of. X to the n. Maybe there's a fast way to evaluate polynomials of that form. And that was the polynomial we needed for RSA. We needed to take the message and raise it to the eth power. That's the polynomial x to the e. So we don't need a fast way to evaluate an arbitrary polynomial. We only need a fast way to evaluate special polynomials like this. So let's take the polynomial x to the n. For definiteness, let's say n equals 100. So we're going to write 100 in base 2. So that's what the little subscript 2 means in the number 1100100. And reading from the right to the left, this means when I look at the base 2, the binary expansion of 100, I have no 1s, I have no 2s, I have 1 4, no 8s, no 16s, 1 32nd, and 1 64. And here is how we can multiply quickly. So x times x is x squared. That's 1 multiplication. X squared times x squared is x to the 4th, 2 multiplications. X to the 4th times x to the 4th is x to the 8th, 3 multiplications. Again is x to the 16, that's 4. X to the 32nd is 5. X to the 64 is 6. So it takes me 6 multiplications to get to here. I want to get to x to the 100. X to the 100 is x to the 64 times x to the 32 times x to the 4. So I take my x to the 64, I multiply by x to the 32, that's 7 multiplications. I then multiply by x to the 4, and that's 8 multiplications. So rather than doing it in 99 multiplications, I'm able to do it much faster in just 8 multiplications. Now you might argue that I might have to store a little bit more. There's tricks you can do to cut down on storage so you don't have to store the entire table. You can just keep track of whichever things you need as you're going down. I'm not going to talk about that, but if you're interested, it can be made a little bit better. Let's analyze how good is this in general. So worst case, how many powers of 2 could we have? What's the highest power of 2 we can have if we want to get up to n? So how big could k equal? So if n is about 2 to the k, about how big is k? Yes. It would be approximately the log base 2 of n. And so the runtime, the worst case for us would be is we have to fill out the whole table and multiply everything. So the worst case for us is the runtime is going to be less than or equal to 2 log base 2 of n. Let's say n is 10 to the 400. So how would you handle the log base 2 of 10 to the 400? What's the first thing you would do? So how would you try to figure out what is the log of 10 to the 400? So somebody give me a log law to try to get a feel of 10 to the 400. You got to remember your log laws. You bring the 400 out. It's 2 times 400 log base 2 of 10, right? I can bring out the power. And now, does anybody know a number that's a little bit larger than 10 whose log base 2 we know? Good. And what's the log of 16 base 2? 4. So rather than having to do 10 to the 400 operations, we only have to do 3,200 operations. 3,200 operations, a computer can do that. I'm not worried about doing 3,200 operations. This is the power of fast multiplication. This is the power of adopting the right perspective. Rather than 10 to the 400, we're doing less than 10,000 operations. Very, very doable. This is one of the most powerful ideas I have seen in my career. Okay, so Horner took us from order d squared to order d, and that works for all polynomials. Fast multiplication takes us down to order log of d. That only works for very special polynomials. Not surprisingly, those are the polynomials we use for RSA. So the next ingredient we need is the Euclidean algorithm. So we've talked a little bit about the Euclidean algorithm in the class. This was in chapter 1. This was the key ingredient in proving that if we look at the numbers that are relatively prime to n, that forms a group. We use this to get inverses. So let's talk a little bit about the Euclidean algorithm. So the input is 2 numbers x and y, and we're going to find the greatest common divisor. Well, we might as well assume the numbers are not equal. If x equals y, it's not that hard to find the greatest common divisor. I'll leave that as an exercise, right? So one of them has to be larger than the other. Let's make y larger than x. Not only does the Euclidean algorithm find the greatest common divisor, but it finds numbers a and b such that ax plus by is equal to the GCD of x and y. That's incredible. And it's going to do this very quickly. So it could be a very slow algorithm. And when we first see it, there is the danger that it's going to be slow. But in practice, it turns out to be very quick. And here's how it goes. Let's just adjust the notation a little bit. Let's let R0 equal Y. Let's let R1 equal X. And this is going to stand for remainder. Then we can write R0 as some multiple of R1 plus a remainder. And I claim that the remainder is at least 0 and strictly less than R1. And the reason is if the remainder was greater than R1, then when I want to write R0 as some number of multiples of R1, I didn't have the right number of multiples. It should have been more than Q1. So is everybody comfortable that I can write my number R0 as some number of multiples of R1 plus a remainder, and the remainder is strictly less than R1? Everybody happy with this? This is, okay. I think we can keep doing this. We can write R1 as some number of multiples of R2 plus a remainder. And so on and so on and so on. And we continue until we get to the point where the remainder is either 0 or 1. And if you want, if you get the remainder is 1, you could do it just one more time, and then you would get a remainder of 0. It doesn't really matter. Every time we do this, the remainder has to be at least 1 less than it was a moment before. So if my number is 10 to the 400, worst case, how many steps could this take? So if x is 10 to the 400, worst case, about how many steps could this take? About 10 to the 400. Because every time I do this, I know the new remainder is going to be at least 1 smaller. Eventually, I'm going to get down to 0 or 1, but it could take me a long time to get there. That's the problem. So this will work, but we don't know at this point that it's going to work quickly. Now, what I will leave you as an exercise is to prove that the greatest common divisor doesn't change as we go through this. That if you look at what is the greatest integer that divides R0 and R1, it's the same as the one that divides R1 and R2. And if you look at it, if you divide R1 and R2, then clearly you have to divide R0, because R0 is some multiple of R1 plus R2. Conversely, I can write R2 as R0 minus Q1 R1. So if you divide R0 and R1, you divide R2. So I'll leave it as an exercise for you to prove that as we march down, the greatest common divisor doesn't change. And so the claim is that we can then climb upwards and find some integers a and b such that ax plus by equals the GCD. And so what I want to do now is I want to try to reclaim things here. And so this way I can, write a little bit better. Okay. We should have a blank screen now. Yes. Okay. So let's take y to be, I did 17 and 11 last time. Those numbers good for you? Do you want different numbers? What numbers would you like to find the GCD of? I can do 17 and 11. If you have other choices, let me know. 17 and 11 are good. So let's let y equals 17, x equals 11. So I want to write 17 as some number of multiples of 11 plus a remainder. How many multiples of 11 do I have? 1, and the remainder is going to be 6. So then I can write 6 as some number of multiples, I'm sorry, not 6. I write 11 as some number of multiples of 6 plus a remainder. How many multiples of 6? It's 1 multiple of 6 plus a remainder of 5. I can now write 6 as some number of multiples of 5 plus a remainder. It's going to be 1 multiple of 5 plus a remainder of 1. And I could go one more step if I wanted, and I could then write 5 is some number of multiples of 1 plus a remainder, and it would be 5 multiples of 1 plus 0. So here, either this one is the GCD, or if you want, you can view this as the GCD. And the claim is that we can use this to climb upwards to write the GCD as ax plus by. Well, let's start off with the very last line. We have the second to last line, we have 6 equals 1 times 5 plus 1. So we can say 1, the GCD, which is 1, is equal to 6 minus 1 times 5. Now what we're going to do is we're going to replace 5 with the two numbers before, with 6 and 11. So we get 1 is 6 minus 1, and 5 is 11 minus 1 times 6. Everybody see how we got that? We used the equation 11 equals 1 times 6 plus 5 to then write 5 as 11 minus 1 times 6. And because it's the remainder always has a coefficient of 1, which makes this nice. Well, let me fix this algebra. This is 6 minus 11. Minus and a minus is a plus. 2 times 6. So if I've done things correctly, it should be 3 times 6. I have a feeling I've made a mistake somewhere. It's 1 times 6, not 2 times 6. There we go. I knew there was a mistake. There we go. It's 1 times 6, so this becomes 2 times 6 minus 11. And as a check, we can see, yes, good, this still equals 1. And I'm going to write it in decreasing order. So it's negative 1 times 11 plus 2 times 6. So I'm always having the smaller number as the last one. Now I want to replace 6 with the two numbers directly in front of it, the 11 and the 17. So this is going to be negative 1 times 11 plus 2, and 6 is the same as 17 minus 1 times 11. So this is negative 1 times 11 plus 2 times 17 minus 2 times 11. So this is negative 3 times 11 plus 2 times 17, or writing them so that I have a larger number first, it's 2 times 17 minus 3 times 11. This is 34, this is 33, and we do see that it equals 1. So this was a way of showing that we can write the GCD of 17 and 11 as 2 times 17 minus 3 times 11. And I claim that you can always walk up like this. So the last thing today is to just show that it's not going to take too long to do this walk. So if we look at what's going on, we might have, at some stage, Rn is Qn Rn plus 1 plus Rn plus 2. And how large could Rn plus 2 be? It's at most 1 less than Rn minus 1. So it's less than Rn minus 1. So the danger is if every time we do one of these steps, what if the remainder only goes down by 1? Then if your numbers are of size 10 to the 400, it could take you 10 to the 400 times. So here is the big fact. So I claim Rn plus 2 is less than or equal to 1/2 Rn. Every time you do 2 steps, you decrease by at least a factor of 2. So you should try to prove that. So for instance, it is possible that you only decrease by 1. But the claim is if you only decrease by 1, then Rn plus 2 is very close to Rn. And then on the next step, you're going to have a massive drop. Conversely, if Rn plus 2 is a lot less than Rn plus 1, you've already got your massive drop. So you can't have 2 bad cases in a row. So after you have a bad day, you have a good day, right? That's comforting. It's not always true in life, but here we are very fortunate that you can't have 2 bad steps. And so if this is the case, then the question is, how many steps would it take? So 2 times the number of steps. Okay. what can we say about that? Well, every 2 steps we decrease by a factor of a half. So if take 2m steps, decrease by a factor of 1/2 to the m, because every 2 steps you decrease by a factor of 1/2. If I take 2m steps, I decrease by a factor of 1/2 to the m, right? So if we have 1/2 to the m times x is roughly of size 1, then that means we want x to be roughly of size 2 to the m. So m should be roughly how big? So this is exactly what we had earlier, right? So if x is of size 2 to the m, about how big is m? Log base 2 of x. So the number of steps is on the order of 2 times the log base 2 of x. So we can find the greatest common divisor very quickly. It's not going to be, horrible to figure it out. Okay, I'm not going to go through the rest to show that we can actually now implement and we can find E and D quickly. We can find large primes quickly. We still need to do that. I'm going to just stop here as to showing you applications of why do we care about all the stuff we've been doing. I think this is the computer that actually has the audio on, so I will make sure I'm holding this one right now. We've seen applications of group theory. We can now send messages quickly. We can decrypt messages quickly. We've seen multiple ways of proving some of the ingredients we need. We've seen ways to emphasize the mathematical thought process. Be lazy. Prove a special case and then reduce everything to that special case that you know. All right, so this is a good place to stop. Just stop recording.